Hello everyone, welcome to this next video on classical mechanics. In this video we shall derive the Hamiltonian's canonical equations of motion. So in the previous video we saw what is the Hamiltonian operator, and it is depending on the basis set Q containing Qj, Pj and T, where these Qj's, they are the generalized coordinates, these Pj's, they are the generalized momentas, and this coordinate T is the time variable where and here the subscript j varies from 1 to n. So that means we have total n Qj's and total n Pj's in number. So next step is to differentiate this Hamiltonian. So in differentiating this Hamiltonian, we have to differentiate it firstly partially with respect to Qj, and then we have to perform the differentiation of this Qj. So this is the thing using the chain rule. And how many such Qj's are there? There are n such Qj's. So we put the summation and we'll have n terms of this kind. And next we'll take the derivative of this h with respect to Pj's, and then we'll apply the derivative for this Pj, and then we'll take the derivative of h with respect to time, and then we can have the derivative for time. So here these terms are partially and this is the complete derivative. So mark this as equation number 1. Next, what we do, we take another definition for Hamiltonian which we derived in the previous video. So here h is defined to be summation Pj Qj dot minus L, where what is L? L is the corresponding Lagrangian operator and it depends upon the basis set Qj, Qj dot and T, where these Qj's are the only independent coordinates and Qj dot, they are the generalized velocities and are dependent on Qj's. Right, so we can substitute this thing over here and we get this form. So now we can differentiate h with respect completely. So here differentiating it, we'll have h as dh. Then here, because these two terms, because we are to perform the derivative of these two terms, so we have to apply the product rule over here. So keeping the first term as such, taking the derivative of second, and then keeping the second term as such, taking the derivative of first. And how many such terms are there? These are n in number, so we have to apply the summation over here. So that is the differentiation of this first term. And then we have to differentiate L, which is a function of Qj, Qj dot and time. So here again we have to differentiate it partially using the chain rule. So firstly we'll take the derivative of L with respect to Qj and then the complete derivative of Qj. Then we'll take the partial derivative of L with respect to Qj dot and then take the partial derivative of Qj as such as in this term. And then we'll take the partial derivative of L with respect to T and then take the complete derivative of T as in this term. Right. So also we learnt that del L by del Qj dot, that is equal to Pj, and del L by del Qj, that is equal to Pj dot. So we can use these two definitions over here. So this term becomes Pj dot, and the second term and this term over here, del L by del Qj dot, this becomes Pj. So this becomes Pj. So here can you see the first term and the second last term, they cancels with each other. So we are only left with dh is equal to summation Qj Pj, Qj dot Pj, dPj minus summation Pj dot dQj, and the last term del L by del T into dt. So now this is our equation number 2. So here the value of dh is given like this, and in the first equation the value of dh is given like this. So here can we compare the coefficients of dQj in the first equation and in the second equation? Here the coefficient is del h by del Qj. So let us see in the second equation. So here the coefficient is minus the coefficient of dQj, that is equal to minus Pj. So from here we can write this to be Pj dot, that is equivalent to minus del h by del Qj. So comparing the coefficient of dQj, we obtain this term. So now let us compare the coefficients for dpj. Here it is equal to qj, so we'll have written qj dot, so it is qj dot. Let us see the coefficient of dpj in equation number 1. So coefficient of dpj in equation 1, that is equivalent to del h by del pj. So it would be equal to qj dot is equal to del h by del pj. So this is our second equation. And similarly, we can compare the coefficient of dt. So the coefficient for dt here in equation number 2, that is del L by minus del L by del t. So minus del L by del t. And the coefficient here is del h by del t. So we have these two terms. Right? So this is the third equation that we get. So these two equations, this one and this one, they are known as the Hamilton's canonical equations of motion. And obviously, because our n varies from 1 to n, so that means in total we have n such equations. These are the first order equations, right? Differential equations, and these are n such equations. So that means in total we have 2n first order equations of these kind. So this was the easiest derivation for this Hamilton's canonical equations of motion. I hope you understood the concept. Well, that is it for this video. In the next video we shall see an example in which we derive the equations of motion using this Hamilton's canonical equations of motion. Thank you for watching.